What specific problem does your method aim to solve related to the use of LLM embeddings in regression tasks?
The method presented in the paper aims to address the underexplored potential of using large language model (LLM) embeddings for regression tasks, particularly in contrast to traditional regression techniques that rely on handcrafted features. Specifically, it investigates how LLM embeddings can serve as robust features for regression, especially in high-dimensional spaces where traditional methods often falter. The paper highlights that LLM embeddings maintain strong regression performance even with increased degrees of freedom, while traditional representations struggle. Additionally, it examines the emergent behaviors of LLM embeddings, such as their Lipschitz continuity and smoothness, which are crucial for effective regression modeling. Ultimately, the research seeks to demonstrate that LLM embeddings can provide a more effective and flexible approach to regression tasks compared to conventional methods.
Can you explain how the proposed embedding-based regression method works? Please illustrate it step by step.
The proposed embedding-based regression method operates through a series of systematic steps. First, it begins with the input data, which is represented as a string and tokenized into tokens, forming a soft prompt that is then processed through a transformer model to generate a high-dimensional output. This output is pooled down to a fixed-dimensional vector, referred to as the LLM embedding, which serves as the feature representation for the regression task. Next, this embedding is fed into a downstream predictor, typically a multi-layer perceptron, MLP, which is trained using a loss function such as mean-squared error to make predictions based on the training data. Finally, the performance of this embedding-based approach is evaluated against traditional regression methods, demonstrating its robustness, especially in high-dimensional spaces, and its ability to maintain smoothness and continuity in the embedding space, which is crucial for effective regression modeling.
Provide a simple example that demonstrates how your proposed algorithm uses LLM embeddings for regression. What key steps can you highlight with this example?
To demonstrate how our proposed algorithm utilizes LLM embeddings for regression, consider a simple regression task where we aim to predict a numeric output based on a set of parameters represented in a JSON format, such as param1 value 1, param2 value 2. The key steps in this process include, first, tokenizing the string representation of the input parameters into tokens. Second, obtaining a soft prompt through vocabulary lookup. Third, applying a forward pass of a transformer model to generate a high-dimensional output. And finally, pooling this output down to a fixed-dimensional vector that serves as the LLM embedding. This embedding is then fed into a multi-layer perceptron, MLP predictor head, which is trained using a loss function like mean-squared error to optimize the regression performance. Notably, this approach allows for leveraging the semantic richness of LLM embeddings, which can outperform traditional feature representations, especially in high-dimensional spaces.
What theoretical or practical benefits did you observe using LLM embeddings for regression as opposed to traditional feature representations?
The paper highlights several theoretical and practical benefits of using LLM embeddings for regression compared to traditional feature representations. Firstly, LLM embeddings demonstrate dimensional robustness, maintaining strong regression performance even in high-dimensional data scenarios, while traditional methods like XGBoost and MLPs tend to falter under similar conditions. Secondly, LLM embeddings preserve Lipschitz continuity and smoothness in the feature space, which is crucial for effective regression, as it allows for better generalization and continuity in predictions. Additionally, the study found that factors influencing language understanding, such as model size and pre-training, have nuanced effects on regression performance, indicating that LLM embeddings can adapt more flexibly to various tasks. Lastly, the results suggest that LLM embeddings often outperform traditional representations in real-world tasks, particularly those with higher degrees of freedom, showcasing their practical advantages in diverse regression applications.
How did you validate or test the efficacy of your proposed method? Can you describe the experimental design and the metrics used?
To validate the efficacy of our proposed method, we conducted a series of controlled experiments using both synthetic and real-world regression tasks. For synthetic tasks, we utilized closed-form objective functions from the Black Box Optimization Benchmarking (BBOB) suite, allowing us to query any input from the input space and assess performance across various degrees of freedom (DOF). In the case of real-world tasks, we benchmarked over 4 families of regression tasks from Google Vizier, ensuring a comprehensive evaluation representative of industry settings. We employed a consistent MLP prediction head, mean squared error loss, and a normalization scheme across all experiments to maintain fairness in comparisons. The primary metric used for evaluating regression performance was the Kendall-Tau ranking correlation, which provided a scale-independent measure of performance that could be aggregated across different tasks.
What were the key results achieved from your experiments, and how do they compare against traditional regression methods?
The key results from our experiments indicate that LLM embeddings significantly outperform traditional regression methods, particularly in high-dimensional spaces and tasks with a high degree of freedom, DOF. Specifically, LLM embeddings demonstrate robust regression performance, maintaining accuracy across varying DOFs, while traditional methods like XGBoost and MLPs struggle as DOFs increase. Additionally, we found that LLM embeddings preserve Lipschitz continuity and smoothness in the feature space, which is crucial for effective regression, a property that traditional representations often lack. Our analysis also revealed that the smoothness of LLM embeddings correlates with improved regression performance, as indicated by the normalized Lipschitz factor distribution, NLFD. Overall, LLM embeddings not only provide better representation for inputs, but also enhance generalization capabilities compared to traditional feature engineering methods.